We're now going to shift gears and spend the remainder of this course studying continuous time stochastic processes. And that word continuous is going to play forefront in our minds. We have already constructed a number of continuous time stochastic processes. In fact, we have a blueprint for doing so. From the Kolmogorov extension theorem, we can construct a Markov process with any transition semigroup that we like. We saw how to construct pre-Brownian motion that way. But we want Brownian motion to be a continuous path process. And as we saw, there are serious problems with doing that from the approach that we took. Let's remind ourselves of those issues. From the perspective of Markov processes, we're really just constructing the overall law of the process. That is, we can construct it as the coordinate process on path space. But I'm going to stop using that term path space for what we used it for before. We just meant the set of all functions from our time set t into the state space S. But those aren't really paths, are they? Because paths implies continuity. So this is just the function space. Now we can always construe any process that we have taking values in a state space S as a coordinate process in S to the t. In other words, the law of that process is a probability measure defined on some sigma field over the probability space S to the t. That probability measure measures for a subset E of S to the t the probability of the set of all paths, omega, where we're identifying omega as a path through this, the path which takes t to xt of omega for each fixed outcome omega, and asking whether that path is in the set E. Now that means that we need to equip our probability space S to the t with a sigma field that contains a whole bunch of collections of functions. Well, the base one that we used when we constructed such measures using the Kolmogorov extension theorem was this minimal sigma field here. That is the sigma field that is generated by all the projections, pi t, which is the same as the coordinate processes themselves. That is, pi t is the map from st down to s, which takes a path omega and spits out the value omega at t. The problem, as we discussed earlier, is that this is a very small sigma field as these things go. It's too small. For example, it typically does not contain this set, the set of continuous paths. So we cannot even ask what is the probability that a path of this process is continuous, is a genuine path. Now we constructed one full stochastic process in continuous time, the Poisson process, and that is not a continuous process, but it is right continuous, and it has left limits. That's another class of functions that we'll be very interested in. And similarly, we cannot even ask the question, what is the probability that the paths of this process are in this set, because it's not typically in this sigma field. Now, we can ameliorate that a little bit. For example, as you'll show on your homework, if we have a process that we know a priori has all of its paths in here, then the set of continuous paths is actually measurable for that process. So with that in mind, one way to proceed would be to expand the sigma field here substantially to contain all of these guys. And once we have all of those guys in there, then the continuous paths will be a measurable subset, and we can proceed from there. There is an approach to doing that, where we build our measures on the space of RCLL paths, but that's a very functional analytic approach, and we're not going to follow it at this time. Instead, we're going to focus on the question of whether we can take a particular process that we've constructed, for example, as a Markov process, basically meaning that we only know this law, and modifying it, creating a version of it that actually lives in the space of continuous paths. Now let's be precise about what that modification or versioning means. Given two stochastic processes, x and y, both indexed by the same time set, doesn't have to be continuous here, it can be general, both taking values in the same state space. We say that they are versions of each other, or y is a version of x, or sometimes a modification of x, if for every particular time t, the event that xt and yt are equal has probability 1. In other words, the probability that xt is not equal to yt is 0 for each individual t. So you might think that that is a natural notion of equivalence for stochastic processes. And it is. You can check that it's an equivalence relation. But it is not the strongest kind of equivalence that you might want to have for them. Because, for example, if t is uncountable, we could also ask about whether xt equals yt for all t. And that will be a different question to the question of whether this is true. See, if t were a countable set, then these two notions would be the same, because a countable intersection of probability 1 events is a probability 1 event. But if t is uncountable, we could well have this be less than 1. In fact, we'll see an example of that shortly. But before we do, let's introduce the stronger notion that says that you really can't tell the difference between the two processes, even at the path level. And that is the notion of indistinguishability. We say that x and y are indistinguishable processes if the probability that x does not equal y is equal to 0. Now, what I mean here is the entire process x and the entire process y. So that is to say, this is the probability of the event that there exists some time where xt is not equal to yt. Now, notice that what that is saying is exactly, we're taking the probability of the union over all t of the event xt not equal to yt. And now we have a bit of a problem. If t is countable, then this is just less than or equal to the sum of the probabilities of those events, and we get back to where we were with versions of each other, because probability measures are countably additive objects. But if t is an uncountable time set, for example, the positive real line that we're going to be dealing with mostly going forward, not only does that argument not work, but we have a more fundamental problem. We don't even know if this is a measurable set. Whatever sigma field we're working in, it may not be closed under arbitrary unions. It's only required to be closed under countable unions. So, as stated, this doesn't even make sense. We have to be a little more careful. We really say x and y are indistinguishable if the outer measure of that is 0. Outer measure, remember, is defined everywhere. Now, if you don't want to go back and review all of your notes, I don't want to give you the definitions again right now, but I will tell you an equivalent formulation of this, which is to say x and y are indistinguishable if and only if there is a measurable null set, a set in the base sigma field that has probability 0, such that the event that x is not equal to y, the event that there's some time where they're not equal, is contained in n. So if this sigma field here was null complete, then this outer measure would equal the measure, and we would have that this is a measurable set. You can see that things get complicated measured theoretically quite quickly when you try to ask these kinds of questions. One thing that we can see easily is that indistinguishable processes are versions of each other. And that's just because if x and y are indistinguishable, then for each fixed t, the event that xt is not equal to yt is certainly contained in the event that x is not equal to y. Because this is the event that there exists some time where they are not equal, and here we're saying, well, the particular time t is one of those examples. So if x and y are indistinguishable, that means that this is contained in a null set, which means that this, which is a measurable set, is null. And that is to say that x and y are versions or modifications of each other. Now, to put things in a quantitative form, let's just note that if our state space is actually a metric space, and we're going to henceforth assume that going forward so that we can actually do some analysis here, and then we'll naturally take the sigma field on the state space to be the Borel sigma field, then to say that x and y are versions of each other is exactly to say that the probability that xt is not equal to yt, well, that's supposed to equal 0 for every t. In other words, the supremum of this over all t is equal to 0. And that's the same thing as the supremum over all t of the probability that the distance between xt and yt is greater than 0. On the other hand, to say that x and y are indistinguishable is to say that the event that the supremum over t in t of the distance between xt and yt is positive. That event has probability 0, but again, that event may not be an event, so we have to take the outer measure in order for that to make sense in all cases. So the difference between indistinguishability and being versions of each other is whether this supremum is on the inside or the outside of the probability measure or outer measure. Now, again, to drive home the point that these really are different notions, let's look at a particular simple example that shows how different they can be. Let's take our probability space to be the standard probability space, the unit interval equipped with the Borel sigma field, and the Lebesgue measure, the uniform probability measure, that is. Now, I'm going to construct two stochastic processes here. One is extremely boring. Xt is the zero process. It's equal to 0 for all t and for all outcomes. Whereas yt is the following. It's equal to 0 most of the time, but yt of omega is equal to 1 if and only if omega equals t. You see, the time interval t, where these are defined, is the unit interval as well, which happens to be the probability space that we've formed. Now, for each fixed t, the event that xt is not equal to yt, well, since xt is 0, that's the event that yt is non-zero. Well, we see where yt is not equal to 0. This is the probability of the set of all omega, where omega equals t. That is, it's the Lebesgue measure of the singleton point t, which has probability 0. And so that shows us that, therefore, xt and yt are versions of each other. But are they indistinguishable? Well, the event that x is not equal to y, as processes, which is the event that there is some time in the unit interval where xt at the outcome omega is not equal to yt at omega. That's the set of all omega, so that there is some time t where the indicator function of the event that omega equals t is not the 0 function. But for every omega, there is some t so that this is not the 0 function. It's always equal to 1 when omega equals t. So this is true for every omega. This is the full probability space omega, and therefore the probability that x is not equal to y is actually equal to 1. So these are not indistinguishable. They are very distinguishable. Now that may look like a silly, contrived example, but we will see natural examples in the wild later on of processes that are versions of each other, but are distinguishable as processes. Let me note, however, that that's an exclusively continuous time phenomenon because, as we intimated on the last slide, if we have a countable collection of times, index say t1, t2, t3, etc., and if two processes xt and yt are versions of each other, then the probability that there is some time in that list where they're not equal, well, that's the probability of the union over those countably many times of the event that xtn is not equal to ytn. but that is less than or equal to the sum over those countably many times of the probability that xtn is not equal to ytn. All of those have probability 0, and that countable sum is therefore 0. And so what we see is that if the whole time set is countable, then being versions of each other is the same thing as being indistinguishable. And more generally, if you have two processes that are versions of each other, then they always agree with probability 1 on any countable collection of times, in particular on any finite collection of times. And so that is to say, if two processes are versions of each other, then they must have the same finite dimensional distributions. Now, thinking back to Markov processes, when we constructed them at the beginning, we basically just specified them by their finite dimensional distributions. We constructed our Markov process as a family of probability measures on this probability space. The function space from t to s, equipped with the minimal sigma field with respect to which the coordinate process is measurable. And then this family was indexed by all possible starting distributions. They all shared the same common transition kernel, making them into Markov processes, and that showed us how to compute the finite dimensional distributions. Conversely, using the Kolmogorov extension theorem and using the nested structure that the Markov property gives to the finite dimensional distributions, starting with the finite dimensional distributions, we could construct this family of measures. But that whole construction didn't tell us anything about the path properties. We can't even ask the question whether the paths of such processes have regularity like continuity or right continuity in this context. So what we're going to do as we proceed forward is to show that under certain circumstances, after we construct one of those Markov processes as such a family of measures, once we have a construction of the process, we can then find a version of that process whose paths are continuous. Now, that's not always true, of course. The Poisson process has no continuous version, as you can intuitively understand, and as we'll prove in a few lectures. But when we can do it, this is what we'll mean by saying that a particular Markov process has almost surely continuous paths. What we literally mean by that is there is some version of the process that has continuous paths everywhere. And since versions have the same finite dimensional distributions, it will be the same Markov process. It will have the same Markov transition kernel and same family of probability measures indexed by starting distributions. But now, instead of constructed on the function space s to the t, it will be constructed on the space of continuous paths from t to s, which is a strict subset of this space. This is what we will call path space going forward. But even so, that path space is still a little bit too big for some of the constructions that we're going to do. So let's drill down a little more precisely. We're actually going to construct our processes on spaces of Hölder continuous paths. So if I have some path, omega, from, say, the positive real line into a metric space, that is, omega is in s to the 0 infinity, for any fixed number alpha in the open unit interval, we say that that function omega is Hölder alpha continuous, written like this, if there is some constant, which of course depends on the function omega itself, such that for any two times s and t, the distance in the state space between omega of s and omega of t is controlled by the distance between s and t, but that distance is going to be measured in this funny way, s minus t to the alpha. Now, if alpha were taken equal to 1, which we're not allowing in this definition, then what we get here is exactly the definition of Lipschitz functions. But we don't include alpha equal 1 because then we would have colliding notation. C1 here would mean Lipschitz functions, but that's not what we usually denote by C1. C1 is continuously differentiable functions, at least in the case where S is R or RD, where that notion makes sense. So that's one reason why we reserve alpha less than 1. Of course, we could also ask, why not allow alpha to be bigger than 1? Well, as you're going to show on your homework, if this condition holds for any alpha bigger than 1, then the path omega is actually just constant. So we really can't be Hölder 1.5 continuous. Now, just to highlight one nice property of these Hölder continuous function spaces, they are nested, at least if we restrict our time interval to a compact interval. If alpha is less than beta, and omega is a C beta function on that compact time interval, then it's a C alpha function. That is, it's harder to be C beta continuous when beta is bigger than alpha. And the reason for that is quite straightforward. If I just compute s minus t to the beta, I can write that as s minus t to the alpha times s minus t to the beta minus alpha. And on our compact time interval, s minus t is no bigger than the width of the interval. So that's less than or equal to t to the beta minus alpha times s minus t to the alpha. So that shows us that if omega has distances less than or equal to a constant times this, then they're also less than or equal to a constant times this positive constant times that, showing this inclusion. Now, the reason we're going to work with these spaces is twofold. First, there's a nice computational way that we'll be able to measure inclusion in these spaces from a countable dense subset of the time domain. And that's going to be necessary to work with the measure theoretic constructs we're familiar with. The other reason is it turns out that the processes that we know and love, like Brownian motion that we're about to finally fully construct, actually are this regular for some alphas. And that's better than being just continuous. So we may as well be as precise as possible about how regular the paths of those processes are. Now here's our game plan. In the next 2 lectures, we're going to present criteria in terms purely of the finite dimensional distributions of a stochastic process, which guarantee that the process has a C alpha version for some alpha. Those criteria are due to who else? Kolmogorov. And in order to understand and even state those criteria, we first need to take a diversion to the land of dyadic rational numbers.